and welcome to this video. As promised, I'm going to prepare a separate video in addition to the live class that we have of the same slide that we have for lesson 3.8 Polynomials. Welcome to lesson 3.8 Polynomials, the first lesson for the final term. And in this section, we're going to cover the entirety of chapter P.3 of the material that we are using for the class. For those who don't have a copy, you may check the Google Classroom so that you can download a PDF copy of our module. Also, for those who did not attend the live class, this is the only discussion that we're going to have. I will try to slow down with the discussion, but if there's something that you find difficult to understand along the way, you can pause, you can rewind, you can repeat watching the video over and over until all of the difficulties are dealt with. If you have questions, you can clarify, you can ask them in the comment section, and I will make it a point that each of the questions will be answered thoroughly. Okay, so let's proceed. In order for us to understand, our lesson is about polynomials. This is a typo error. What are polynomials? How do you operate on polynomials? So operations on polynomials. In order for us to proceed with understanding polynomials and operating on polynomials, we need to understand the fundamental component that constitute a polynomial. That is a monomial. A monomial has three types and one qualifying definition. What are the three types of a monomial? A monomial first can be a constant. So when we say a constant, we're also referring to a number. Any number could be a monomial. If it's 5, it's already a monomial. If it's 100, it's already a monomial. A constant is a symbol with which the quantity associated with it does not change. It's consistent all throughout contexts of mathematics. So -8 is a constant, 9, 0.5 is a constant. It could be used, or it is a monomial. We have 1/2, it's a monomial, and pi is also a monomial. How about the second type of monomial? It could be a variable. So when we say variable, it's formally defined as a quantity that may change within the context of a mathematical problem or experiment. Say you have a variable for one problem and the quantity for that variable is 20 for that problem. When that same variable appears in another problem, it may or may not be 20 anymore. It could be 40 or any other quantity, but the same variable, hence the name variable, because the quantity associated with the symbol varies, and usually the symbol that we use for variable are letters. The most common of them, the frequently used variables or symbols for variables are x, y, and z. So an x is already a monomial, or a y or a z. You can also have a combination of a constant and one or more variables. And when we combine in writing a constant and a variable or more variables, we denote the operation multiplication on it. So let's say constant. Okay, let's have an example here. A constant multiplied with a variable. So 2x, 2 times x. We have 4xy. In here we have more than one variable. We have variables x and y. We have x, y, and z, 3 variables. And the last qualifying definition is, if we have a variable and that variable has an exponent other than the default exponent 1, then Such a variable can only be considered a monomial if the variable has non-negative integer exponents. So non-negative and integer exponents, meaning no negative exponents are allowed, zero exponent is allowed, and no rational exponents are allowed. So only integer exponents are allowed. Let's have an example here. So constant times a variable with positive integer exponents or with zero exponent. I need to remind that it's not always constant and variable. Sometimes it's just variable, and it could still be considered a monomial. So we have 2x squared, a constant 2, multiplied with a variable x raised to a non-negative integer exponent 2. So this is an example of a monomial. Second one, we have 1/2 y cubed, also a monomial. We have 0.5 x squared y cubed z12, also a monomial. Let's have a drill, and let's try to identify whether the following examples are is a monomial or not. First one, we have 5xy. Is it a monomial or is it not? Pause first and then answer and then play to hear the correct answer. Are you ready? In 3, 2, 1, it's a monomial. We have 5, a constant. We have x, y. Their exponents are, and although you cannot see the exponent of x and the exponent of y, it's by default 1. 1 is non-negative and it's integer, so 5xy is a monomial. Next, -8z squared. Is it a monomial or not? Pause and then answer. Okay, ready? In 3, 2, 1. -8z squared is a monomial. Although there is -8, but still the negative sign is in the coefficient. The exponent, if we're going to look at it, it's still non-negative because it's positive 2, and it's integer because it's a whole number. Third example, we have 3 raised to -2 x cubed y to the 4th. So is this a monomial or not? Pause, answer, and play if you want to know the correct answer. In 3, 2, 1, this is monomial. Although there is -2 as an exponent, but the exponent is in the coefficient, not in the variable. It only becomes not a monomial if -2 is in either x or y. But if we're going to inspect closely, x has 3 and y has 4 as exponents, and they're non-negative and they're integer exponents. Next, we have 1/2 y raised to 3/4. Is this a monomial or not? Pause, answer, and then play if you want to hear the answer already. In 3, 2, 1, this is not a monomial. Why? Because the exponent of the variable y is 3/4, non-integer. It's rational number. It's a non-integer rational number. It's fraction. Next, we have 0.75 x raised to -2 y cubed z12. Is this a monomial? In 3, 2, 1, this is not a monomial because x, one of the variables, x, y, and z, x has a -2 for an exponent. Hence, this is not a monomial. Okay, so let's dissect the parts of a monomial. We have 3x cubed y to the 4th z. The letters x, y, and z, we call them the variables. We already know that. But the number 3, we call this the numerical coefficient, or simply put, coefficient. Most people refer to it just as the coefficient, but well, if you wanna be more accurate, you can use numerical coefficient as a name to refer to the number 3 or any number before variables or with the variables in a monomial. Now let's try to identify the coefficients for the following. We have 5xy. In 3, 2, 1, coefficient is 5. Next, we have negative 8z squared. What's the coefficient for this? Yes, you guessed it right. In 3, 2, 1, coefficient is negative 8. Next, negative x cubed y to the 4th. What's the coefficient in here? Pause, answer, and then play if you want to know the correct answer. Or if you want to proceed, of course, you want to play because you don't want to end in here. The hidden coefficient not indicated there is in front of the x, it's 1. If a number is not indicated in a monomial, there is no constant in a monomial. Automatically it's 1. And we have a sign there, so it's negative. Therefore, the coefficient is negative 1. Lastly, we have y cubed. And also, you can't see a number in here, but the coefficient here is positive 1. Let's proceed. Now, in the future, we would need to use the information of a degree of a polynomial as a basis for other operations that we want to do with expressions containing monomials. So, how do you identify the degree of a monomial? The degree of a monomial is simply the sum of the exponents of the variables. Again, it's the sum of the exponents, so you're going to add the exponents of the variables only. And sometimes, in order to confuse you in the quiz, the coefficients of variable have exponents as well, but you don't need to add up the exponent of a coefficient. So we have, if we're going to identify the exponents in here, we have, the coefficients, the number that you're going to use if you're going to compute, if you're going to add up the exponent, the coefficient will have 0, although their exponent is 1, but automatically the number that you're going to use for coefficient is 0 because the degree of a coefficient is 0. So we have 0 plus 3, that's the exponent of x, plus 4, the exponent of y, plus 1, the hidden exponent of z, is equal to 8, and 8 is the degree of this monomial. Again, the degree of 3 is 0, the degree of x is 3, the degree of y is 4, the degree of z is 1 because its exponent is 1. Therefore, the degree of the entire monomial is 8. Now, let's try to identify the degree of the following monomials. We have 5x cubed, y squared. What's the degree of this monomial? This is very simple. It's 3 plus 2, which is 5. The degree is 5. Next, we have negative 8a squared, b squared, c cubed, d fifth, e7. You have 5 variables in here. So what's the degree? Simply add the exponents of the variables. So from left to right, we have 2 plus 2, 4, plus 3, 7, plus 5, 12, plus 7, 19. So the degree of this monomial is 19, 1, 9. Next, what's the degree of this expression? Negative x cubed y to the 4th, so that's 3 plus 4. The degree is 7. And we have y cubed z7. The degree is 3 plus 7, 10. Let's up the difficulty with drill 2. In drill 2, questions are a little bit, a tad challenging compared to drill 1. So we have 2x squared multiplied with the quantity x y squared to the fifth. So in order to decide for the degree of this, you need to simplify this first using the skill that you acquired in the previous lessons, or using the concepts that we talked about in the previous lessons. So simplifying, first the one inside the parenthesis first. So we're going to distribute the exponent outside the parenthesis, that's 5, by multiplying it to the individual exponents of the variables inside the parenthesis. So we have x times 5 is 5y squared times 5 becomes 10. So x to the fifth to y to the 10th, that's 15 inside the parenthesis, plus 2 outside the parenthesis, the x squared. So that gives us 17. Therefore, the degree of this monomial is 17. That's 1, 7. Next, we have 3 squared y cubed multiplied with the quantity x squared yz cubed. Let's focus first on what's inside the parenthesis. Let's distribute the exponent outside the parenthesis, that's the 3, onto each of the exponent of the variables inside the parenthesis. So we have x squared times 3 becomes x to the 6th, y to the 3rd, z to the 3rd. So that's 6 plus 3 equals 9 plus 3 equals 12 plus 3 outside because we have y cubed outside. So 12 plus 3 is 15. It's not 17, it's just 15 because the square or the exponent 2 and 3 is not counted. 3 is a coefficient, therefore 2 will not be counted. So it's just 15. So it's 3, 6, 12, 15. Okay, the degree of the second monomial is 15, 1, 5. Third, we have 4 squared again. Or later, if you want to answer, I'm not going to spoil it for you. By the way, this is a typo. It's a squared inside the parenthesis. So outside we have 4 squared a squared b cubed multiplied with a squared c cubed raised to the quantity raised to the power of 2. So let's deal with what's inside the parenthesis first. So 2 and 3 becomes 4 and 6. So the degree inside the parenthesis is 10. Outside we have 5, so it's 15. So the degree of the third monomial in this drill 2 is 15. Let's come now to what we've been preparing. Okay, let's come now to what we've been preparing by talking about monomials. That is the polynomial. The polynomial is a sum of a finite number of monomials. So we have two things here to remember. First is we add up the monomials, the sum of the monomials. And the second is there are a finite number of monomials. So the number of monomials included in a polynomial expression is limited. You can count it, it's countable. It's not infinite, okay? It's finite. So let's have an example here. We have 3 plus 2x squared minus 3y to the 4th minus x cubed y to the 4th. Looking at it, you'd see that there's 3 plus 2x squared. So that's sum of monomials. But we have minus 3y to the 4th minus x cubed y to the 4th. And you're inclined to ask, if the definition holds true, why are there subtraction in here? And that's a pretty much valid complaint and observation. But remember that an expression, a subtraction can be expressed in terms of addition, because subtraction is simply the inverse of the addition. And this polynomial can be rewritten such that all of the terms in here are combined with the addition operation. So this is the, if we're going to rewrite it, and if we're going to add all of the terms instead of subtracting the third and the fourth terms, we have 3 plus 2x squared plus becomes positive, and the minus becomes the sign of the third monomial and the fourth monomial. So plus negative 3y to the fourth plus negative x cubed y to the fourth. So notice how easily we can convert a polynomial with subtraction in it into an expression with purely addition on it. Each monomial here, we have 4 monomials. They're called a term of the polynomial. So if we're going to count the number of terms in here, we have 1, 2, 3, 4. So this one has 4 terms. So let's explore a second idea. Earlier we were able to compute for the degree of the monomial by adding the exponents of the variable in the monomial. How about the degree of the polynomial? How do you compute for the degree of the polynomial? Because there are multiple monomials in there, which degree are you going to use? So the degree of the entire polynomial is the greatest of the degrees of the terms. In here we have, in the example that we have here, we have 4 terms. First term is 3. Second term is 2x squared. Third term is negative 3y to the fourth. Fourth term is negative x cubed y to the fourth. And if we're going to compute the individual degrees of each of the term, we will have 0 for 3 because always the degree of a coefficient is 0. 2 for 2x squared because the exponent of x is 2. 4 for the third, and 7 for the fourth term in here. Now, based on the definition of the degree of the polynomial, which is the greatest of the degrees of the term, we can immediately identify the degree of the entire term. The highest is 7. Therefore, the degree of this term, of this polynomial, is 7. The degree of the entire polynomial is 7. Let's try to identify, using drill 1, the degree of the following polynomials. Let's begin with easy because this is drill 1. We have 2x squared y to the fourth plus 3xy plus 4y to the seventh. Let's identify the degree of each of the monomial involved, or the term. We have 2 plus 4 is 6 for the first term. For the second term, we have 1 plus 1 is 2. For the third term is 7. So the highest is 7. The term of the entire polynomial is 7. Next, we have 4 raised to 8, a squared b cubed plus c raised to 7 plus b squared c to the fourth. Now I'm going to give you some time to solve this. And you can pause the video so that you can answer. If you have the answer now, you can continue in 3, 2, 1. Okay? So let's identify the degree of each of the terms first. First one is 2 plus 3. We don't add the 8 because 8 is the exponent of the 4. 4 is a coefficient. So 5. The second one is 7. The third one is 6. The degree of this is 7. Next, we have negative 3m cubed n squared minus n to the fifth plus m to the fifth. You can pause, analyze. If you have the answer, you can play again. In 3, 2, 1. Okay, let's identify the degree of each of the term. The first term, we have 3 plus 2, that's 5. The second term is 5. The third term is 5. All of them are 5. What's the greatest? Of course, it's 5. So the degree of the entire polynomial is 5. Let's have drill number 2. Identify the degree of the following polynomials. We have 3 times the quantity x squared y squared cubed plus 2x cubed times the quantity x squared y raised to third power. The entire quantity raised to the third power. So first is we need to simplify this. We need to distribute the exponent outside in the first term to the exponent inside, giving us with x to the sixth, y to the sixth. So the first term has a degree of 12. The second one, we have x to this inside the parenthesis, x to the sixth, y to the third, multiplied with the variable, or we can add the exponent outside. So it's 3 plus 6 is 9 plus 3 is 12. 12 is the highest, so the degree of this polynomial is 12. Next, we have 2 times the quantity x squared minus y cubed squared. Now there's a tricky part in here because we cannot immediately distribute 2 inside the exponents of the variables inside the parenthesis, because the operation involved is subtraction. So we need to multiply x squared minus y cubed with x squared minus y cubed first. And if you already did that, or if you haven't done that yet, you can pause this video. But if you're done, you can continue. So multiplying the highest exponent in the variable, the term with the highest degree is that's y cubed times y cubed, that's y to the sixth. So the degree of this expression is 6. Okay, let's continue. So using the same example that we had earlier, so 3 plus 2x squared minus 3y to the fourth minus x cubed y to the fourth. The sign of a term is the sign that precedes the term. So let's identify the terms first. We have 3, 2x squared, negative 3y to the fourth, x cubed y to the fourth, negative. So the sign of a term is the sign before the term. That precedes. That's what precedes means. The sign before the term. So in 3, there is no sign. It's implied, it's positive. In 2x squared, the sign before it is plus, so it's positive. In 3y to the fourth, the sign before it is negative. And lastly, the sign is negative. So in most operations involving polynomial, it's crucial that we gain the skill in identifying like terms. So what are like terms? Like terms are terms within the variable with exactly the same variables raised to the same power. So 2 things. Each term must have the same variable. Let's say they have the same exact variable. Nothing is missing. Same exact. If the first term has AB, the second term must have AB as well. Or if the first term has ABC, the second term must have ABC, not just AB or A. It should be ABC. And the second requirement for them to be called like terms is that each of the variable will have exactly the same exponent. So if A on the first term has 2 as an exponent, the A on the second must have 2 as well in order for both to be considered like terms. All of the variables in each of the term will have the same exponent as with another in order for them to be called like terms. Let's have an example for that for us to make that easier. So let's have this one as an example. We have a squared plus 2a squared b squared minus 4a times a minus b squared multiplied with the quantity 3a squared. Identifying the before we can proceed with this, because it's a bit confusing, you need to simplify this first. You need to remove the parentheses. So rewriting gives us a squared plus 2a squared b squared minus 4a squared minus 3a squared b squared. Now that we did that, now that we simplified it, it's easy to identify which of the terms have exactly the same variables raised to the same power. Observing, you would know that the first term and the third term has a only a as a variable, irregardless of the coefficient. We're not looking at the coefficient when we decide for like terms. So the first term and the third term has a as a variable. And second is, notice that a is raised to the second power on the first term and second power on the third term. They have the same exponent, same variable, same exponent. Thus, the first and the third are like terms. Similarly, the second and the fourth have both a and b. Nothing is missing in either. AB on the second, AB on the fourth. Also, the a and the b have the same exponent in the second and in the fourth terms. You have 2a squared b squared, and in the fourth you have 3a squared b squared. Same variable, same exponent. Their coefficients may differ, but we don't look at the coefficient. The coefficient 2 and negative 3, they differ, but we don't look at it. So therefore, terms 2 and 4 are like terms. Now, how do you use like terms? Why do we talk about like terms? Because we use the concept of like terms to convert a polynomial into its simplest form. So, how do you convert a polynomial into simplest form? You simply combine the like terms. In the previous example that we had, we have a squared plus 2a squared b squared minus 4a squared minus 3a squared b squared. The first and the third terms are like terms. The second and the fourth are like terms as well. So how do you combine? You simply combine their coefficients. In the first and the third term, we have coefficients 1, positive 1, and negative 4. 1 minus 4 is negative 3. And then you write down exactly the variable with the exponent a squared. So negative 3a squared. The second and the fourth have coefficients 2 and negative 3. 2 minus 3 is negative 1. So it's negative a squared b squared. So this expression in black is in its simplest form. It cannot be reduced any further into a simpler form because this is the simplest. So let's have a drill. Reduce the following polynomials to its simplest form. So we have 2ab plus b squared c plus c times b plus 2b times a. We need to remove the parentheses first on the third and the fourth terms, giving us with c b squared and 2ab. Now, notice that if we're going to follow the order, it becomes cb squared and 2ba. Irregardless, without much regard, regardless and irrespective and regardless of their order, as long as they have the same variables with the same exponents, they are like terms. So observing, you have second term is b squared c, the third term is c b squared. Different order, but the same variable with the same exponent. Therefore, the second and the third terms are like terms, and that we can combine them. The first and the fourth have the same situation. It's 2ab, but the fourth is 2ba. Different order, but same variable with same exponent. So the first and the fourth are like terms that we can combine. Let's begin with the first and the fourth. 2 plus 2 is 4, so it's 4ab plus 2b squared c. That's the answer. 4ab plus 2b squared c. Let's have the next. So we have 2x squared y cubed plus 3y squared minus xy squared times 3xy. We need to get rid of the parentheses first in order to judge it more accurately. So in the parentheses, we have, if you're going to multiply them, it becomes 3x squared y cubed. 3x squared y cubed. and the variables and the exponents match exactly that of the first term. So the first and third terms are like terms. So we have coefficient -3 on the third term, +2 on the first term. Combining them gives us -1. So it's negative x squared y cubed plus 3y squared. We cannot have a negative leading coefficient. Let's turn it into positive. So it's or we could rearrange. It becomes 3y squared minus x squared y cubed. Okay, so 3y squared minus x squared y cubed. Let's try to simplify it further by using the correct sign later on. Let's have drill number 2, something that's a little bit more challenging than the usual. So first is we deal with the exponents. We have 3x times x squared y squared to the third. So simplifying, we get 3x to the 7th, y to the 6th. I'm gonna use a piece of paper here. You can only follow this video if you're computing it as well. So it becomes 3x to the 7th, y to the 6th, plus 4x squared y squared, plus 2x to the 7th, y to the 6th. So the first and the third terms are like terms, and we can combine them. 3 plus 2 is 5. So it becomes 5x to the 7th, y to the 6th, plus 4x squared, y squared. The correct answer is 5x to the 7th, y to the 6th, plus 4x squared, y squared. You can verify it with, if you have objection, you can raise them down in the comment section and we could deal with them. We could answer your questions or objections. Now, if you have noticed, seems like when we write a polynomial, we have disregard for a correct order. Now, mathematicians have proposed what's called a standard form of a polynomial, in which the terms inside a polynomial will be arranged according to a formula prescribed by the standard form. And the standard form is standard form of a polynomial of degree n. This is degree n. And the variable is a n x to the n plus a n minus 1 x to the n minus 1 and so on. So this formula allows you to achieve the standard form by rearranging the terms in the polynomial such that the term with the highest degree is first on the order, and the term with the lowest degree, usually a coefficient because the degree of a coefficient is 0, is on the last order on the right. So you simply rearrange based on the degree of a term, where the initial coefficient, the first coefficient, cannot be 0 and cannot be negative integer. So when you rearrange a polynomial to fit into a standard form, the first coefficient cannot be negative. How do you deal with the negative coefficient in the first term? You simply convert, you flip, you change the signs of each of the term in the polynomial to its opposite. We call that the additive inverse. So if the first degree has a negative sign, you convert it into positive. All of the signs in the succeeding terms will be changed to its opposite. A positive becomes negative, and negative becomes positive. We're going to explore this later on. So the coefficient a sub n, the first coefficient in a standard form, we call that the leading coefficient, also the constant term. So let's have an example here for polynomial. As we have 6x minus 7 plus 2x cubed. Converting it into a standard form, we're required to place the one with the highest degree first. That's 2x cubed, followed by this the term with the second highest degree, 6x minus 7. So the leading coefficient here is 2. Second one, rearranging, you get negative 2x to the fourth first, followed by 4z cubed plus 3z minus 9. Leading coefficient is 2, negative 2. So what you need to do is to use the additive inverse. Negative 2x to the fourth becomes positive 2x to the fourth minus 4z cubed minus 3z plus 9. You change the signs into its opposite. Lastly, we have y to the fifth minus 3y cubed plus 1 minus 2y minus y squared. Changing it to standard form, we have y to the fifth, because the degree is 5, the highest, minus 3y to the third, degree is 3, second highest, minus 2y, degree is, this is wrong. The next one should be minus y squared. The next one should be negative 2y plus 1. Maybe this is just a typo error. But negative y squared should come first before negative 2y. Maybe I just made a mistake in encoding this. Let's refer to the book later. Leading coefficient is 1. Okay, so let's proceed. I've rewritten this. I've corrected the second example so that the leading coefficient becomes positive. Let's proceed. Now let's simplify and convert to standard form the following expression. We have 2ab plus b squared c plus c times b plus 2b times a. You can pause this, solve, and then play later if you want to know the correct answer. Now if you already finished, you can, I assume that the reason you're here is because you've continued playing the video and you've already solved it. So let's try to simplify and remove the parentheses first so that it's easier to simplify this. And if you do this, you'd realize that the first and the last terms are like terms. The second and the third are like terms as well. So you can combine the first and the last, making it 4ab, and the second and the third, making it 2b squared c. Now 2b squared c has a degree of 3, so it comes first. 2b squared c plus 4ab. Correct answer is 2b squared c plus 4ab. Next, we have 2x squared y cubed plus 3y squared minus xy squared times 3xy. First step is we need to simplify this, and the easiest way to simplify is to remove the parentheses. So it becomes 3x squared y cubed and 2x squared y cubed in the first term is like term. So the first and the third terms are like terms. We can combine 2 and negative 3, giving us with negative x squared y cubed plus 3y squared. Since the leading coefficient is negative, we can convert this by flipping, using the additive inverse, flipping the signs. So it becomes x squared y cubed minus 3y squared. Final answer is x squared y cubed minus 3y squared. Now, how do we add polynomials? We've come at last to adding polynomials. Okay, so first is, when you're adding polynomials, make sure that the polynomial is in its simplest form. That way, adding two polynomials becomes easier. Second is, you add only the coefficients of the like terms. And this is easily done by writing the two polynomials in a column. Let's have an example for you to know this, to understand this much easier. We have 3x cubed minus 2x squared minus 6 plus 4x squared minus 6x minus 7. So we're going to add the two polynomials. The first polynomial is enclosed by a pair of parentheses, and the second one is enclosed by a pair of parentheses. The first step, and this will make things a lot easier, is to write them down in columns and aligning the terms with the same degree, the terms that are like terms. So let's write the first one. We have 3x cubed minus 2x squared minus 6. And then write the second one, aligning it the like terms. So we have 4x squared minus 6x minus 7. You see a gap between 2x squared and negative 6, just so the like terms could be aligned. And now that they're aligned, let's finish this off with the, a symbol here, plus symbol. So let's add the columns accordingly. From the rightmost, we have negative 6 plus negative 7 equals negative 13. Negative 6x will be carried down because there is no term similar to it. Negative 2x squared plus 4x squared is positive 2x squared. And then we bring down 3x cubed. So this is your final answer. Let's have subtracting polynomials. How about subtracting polynomials? How do you subtract two polynomials? First is, and this is required for all polynomials that you want to operate on, you simplify. You convert them into simplest term. Second is you add the additive inverse. Okay, so write them down in a column. Example, we have 3x cubed minus 2x squared minus 6 minus 4x squared minus 6x minus 7. So write them down first. Write the second one, aligning the like terms, and then use the additive inverse. I've already used the additive inverse, meaning since it's subtraction, the second one, all of the signs in the second one will be inverted. So we have 4x squared becomes negative 4x squared. We have negative 6x, it becomes positive 6x. And we have negative 7, it becomes positive 7. Adding them up now that you have the additive inverse of the second polynomial, we have negative 6 plus 7 is positive 1. 6x carry down. Negative 2x squared minus 4x squared is negative 6x squared. 3x cubed is carried down. This is the final answer. How do you multiply polynomials? The first one is you simplify. The second one is you multiply each term of the multiplier with all the terms of the multiplicand. In order for you to better understand it, let's have an example. So 2x squared minus 5x plus 3 in this example is multiplied with 3x plus 4. Write them in the same format that we did for the addition and the subtraction. First is the first polynomial, this one. Second is, we're not going to align the like terms, we're just going to write the second polynomial on the second line, aligning it to the right, like this one. The 4 is aligned with the 3, and the 3x is aligned with the 5. And then you multiply using the 4 first, the last term in the second polynomial. Multiply it with 3, with negative 5x, and with 2x squared. Gives us 4 times 3 is 12, 4 times 5, negative 5 is negative 20x, 4 times 2x squared is 8x squared. Now let's go to 3x, and this will be written on the next line. It's 3x times 3 is 9x, 3x times negative 5x is negative 15x squared, and 3x times 2x squared is 6x cubed. Let's put a line in here and add. We have 12. Negative 20 times plus 9 is negative 11. 8 minus 15 is negative 7 and 6x cubed. So that's it for multiplying polynomials. We could also use a method called the FOIL method, and it's applicable for binomials that follow a format of a plus b and c plus d, meaning there are two terms on the first polynomial and there are two terms on the second polynomial. We call that binomial. Two nomials, two terms. FOIL stands for first, outer, inner, and last. In this example that we have, the first are the first terms. So we have a times c, and then plus we have outer. So the outer is a and d, ad, plus the inner, b times c, plus the last terms, b times d. This method is supposedly powerful in allowing you to mentally compute for the product of two binomials. So let's have an example utilizing the FOIL method. So we have here 7x minus 2 times 5x plus 4. 7x is our a, negative 2 is our b, 5x is our c, and 4 is our d. So let's utilize the FOIL method. First is the f, or the firsts. The firsts is 7x and 5x. So 7x times 5x is, okay. Next is we have outer, so 7x and 4, plus inner, that's negative 2 times 5x, plus last, that's negative 2 times 4, giving us with 35x squared plus 28x minus 10x minus 8. See, simple and fast. Simple, efficient, accurate, fast. Simplifying it further, because we have two like terms here, we have 35x squared plus 18x minus 8. So we always answer with the simplest form. Let's try to have a drill. Multiply the following binomials. So we have 5x plus 5 times 2x squared minus 4x. And we have 4a minus b times 3a plus b. Okay, so let's begin with the first one. We have first, so 5x times 2x squared is 10x cubed, right? Next is outer. So we have outer is 5x minus 4x. That's negative 20x squared. Next is inner. So we have 5 times 2x squared. So that's positive 10x squared. And we have lasts 5 times negative 4x, which is equal to negative 20x. Final answer is 10x cubed minus 10x squared minus 20x. If you think my answer is wrong and your answer is correct, you can outline your solution or mention which part I got it wrong, and in the comment section we could re-explore it. Next, we have 4a minus b times 3a plus b. Firsts, that's 4a times 3a, giving us with 12a squared. And second, we have outer, 4a plus b, that's plus 4ab. Next is inner, negative b times 3a, so that's negative 3ab. And last, we have last terms, negative b times b, or negative b squared. Simplifying, we have 12a squared plus ab minus b squared. Final answer is 12a squared plus ab minus b squared. There are also special products, and in this session we're going to talk about two of the special product formulas. or formulae, depending on what you want to use. By the way, the plural form of formula is formulae or formulas. Both are accepted and correct. So special form, we have sum and difference of the same variable. Meaning, if you have variables x and y, it's x plus y times x minus y. Same variable or same expression. Sometimes it's not just a variable, sometimes it's expression. You will see in the examples later on. If we're going to multiply the sum and difference of the same terms, okay, the product is simply the difference of the square of each of the terms. And for the binomial, if we're going to square a binomial, say x plus y squared, simply you put, there are three terms in the answer. The first term is the square of the first term of the first term of the polynomial is the square of the first term of the binomial. The last term is the square of the second term of the binomial, and the middle is 2 times the first term of the binomial times the second term of the binomial. Or the formula here, if you are confused, just refer to the formula in here. But basically, this is it. Now the x and the y can be replaced with a much more complex expression. Let's try to explore. So let's have the sum and the difference. Let's have an example 1. Let's begin with a simple one. X plus y, x plus y. Does it count for sum times difference, or is it a binomial squared? This is a binomial squared. This is not a sum and difference. It's x plus y squared. So we have x is equal to x, y is equal to y. It does not follow the formula x plus y, x minus y. It follows the formula x plus y squared. So sum and difference doesn't apply in here. Let's have a second example. A plus b times a minus b. Does it follow the formula for the sum and difference? X here is a, y is b, and it follows the formula x plus y, x minus y. Therefore, you can find this. You can find the product using this special form for sum and difference. Now, the third example, we have 2x squared plus 3y times 2x squared minus 3y. Does it follow the sum difference form? You see, the 2x squared here is the first term of the binomial, and the 3y is the second term of the binomial, and in here they're the same. Their only difference is their operation. The first one is sum, the second is difference. You have 2x squared, your y here is 3y. Therefore, it follows the formula x plus y, x minus y. Let's have an example here for the sum difference. B plus 4 times b minus 4. So let's decide, do they follow the formula? Your y here, your x here is your b, and your y here is your 4. And if we're going to replace x for b and y for 4, it's x plus y, x minus y. So it follows the formula. Automatically, you can say that the product of this is the square, is the difference of the square of both terms. So b squared minus 4 squared, or b squared minus 16. Let's have the second example. 2x plus 6 times 2x minus 6. It follows the sum and the difference formula. So automatically, square of the first term of the binomial and square of the second term of the binomial minus on the middle. So 2x squared is 4x squared. 2x, the quantity 2x squared is 4x squared, minus 6 squared is 36. You can pause this if you want to study it further, or play if you understood it immediately. In here, it also follows the formula, so proceed with the product. Square of the first term minus square of the second term. 3a squared squared minus 2b squared. Notice here that 3a squared, the entire 3a squared is assigned to x, and 2b is assigned to y. Becomes 9a to the fourth minus 4b squared. That's how you apply the formula. So let's proceed with the binomial here. 3 examples again. Example b.1, we have a plus b squared. Automatically, what you do is a squared plus 2ab plus b squared. Just follow the formula. Second example, we have 2a plus 3b squared. So the first term of the answer is the square of the first term of the binomial, 2a squared, the quantity 2a squared. The last term is the quantity 3b squared. The middle term is 2 times 2a times 3b, like this, following the formula. Simplifying, we get 4a squared plus 2 times 2 is 4 times 3 is 12, ab plus 9b squared. Example 3, we have 2x squared plus 4y cubed squared. So the first is 2x squared squared, the last is 4y cubed squared, and the middle is 2 times the first and the last. Simplifying, 4x to the fourth plus 16x squared y cubed plus 16y to the sixth. That's the final answer. So that ends our discussion on chapter P.3, the entire thing. I'm going to talk about, before we talk about the next chapter, the next lesson tomorrow, I'm going to proceed with examples of a problem, but I'd like you to study the applications of polynomials ahead so that tomorrow you can immediately relate to it. The lessons are still pretty easy. Expect though that the quiz will be a bit challenging. Okay, so that ends our discussion of polynomials. If you have questions, you can comment down on the comment section below. Thank you for listening. I hope you have a great day ahead of you.